Hello everyone, and welcome. Today we're tackling a foundational concept in electrical circuits, Ohm's law. Understanding this law is crucial for anyone studying electricity as it helps us predict and control how current flows in a circuit. It's truly the ABCs of electronics. Let's start by imagining a simple electrical circuit. Step 1. Diagram description. Our diagram would show a battery acting as the power source connected by wires to a light bulb. The battery provides the push, the wires guide the flow, and the light bulb, when current passes through it, glows. This setup clearly illustrates where our key elements of voltage, current, and resistance are located. Step 2. Identify key variables. In this circuit, we have three main players. Voltage, V. Think of voltage as the electrical pressure, or push, that makes the charges move. It's like the pressure from a water pump pushing water through a pipe. We measure voltage in units called volts, V. In our diagram, the battery provides the voltage. Current. This is the actual flow of electrical charges through the wire, like the flow of water in a pipe. The more charges moving per second, the greater the current. We measure current in amperes, A, often shortened to amps. In our diagram, current flows from the battery, through the wire, and through the light bulb. Resistance, R. This is the opposition to the flow of current. Every component in a circuit, including the wires and especially the light bulb, resists the current to some extent. A higher resistance means it's harder for current to flow, like a very narrow section in our water pipe. We measure resistance in ohms, O. Our light bulb in the diagram provides the main resistance. Step 3. Relevant equations and principles. These three quantities are elegantly linked by Ohm's law, which states V equals I times R. This equation means that the voltage, V across a component, is directly proportional to the current, I, flowing through it, and its resistance, R. It's a powerful relationship that allows us to understand how changes in one variable affect the others. Step 4. Applying Ohm's law conceptually. Let's see how this works. If we keep the resistance of our light bulb constant, if we increase the voltage, use a stronger battery, the current flowing through the bulb will increase, making it brighter. More push, more flow. If we decrease the voltage, use a weaker battery, the current will decrease and the bulb will dim. Less push, less flow. Now, if we keep the voltage constant, same battery, if we increase the resistance, swap for a bulb with higher resistance, the current flowing through it will decrease. Same push, but more opposition means less flow. If we decrease the resistance, swap for a bulb with lower resistance, the current will increase. Same push, less opposition means more flow. This conceptual exploration helps us grasp the direct and inverse relationships within Ohm's law. Step 5. Checking for consistency. The beauty of Ohm's law lies in its simplicity and directness. Our conceptual examples clearly demonstrate the consistent relationships. More voltage means more current for a given resistance, and more resistance means less current for a given voltage. It aligns perfectly with our water pipe analogy. More pump pressure leads to more water flow, and a narrower pipe restricts the flow. Step 6. Conclusion and real-world application. Ohm's law is fundamental for designing and troubleshooting electrical circuits. Electricians use it to calculate the correct wire sizes for household wiring. Engineers use it to design electronic devices, and technicians use it to diagnose problems in circuits. It's how we determine the right resistor to protect an LED from too much current, or how much current a certain appliance will draw from a wall outlet. Step 7. Additional insights and considerations. While incredibly useful, it's important to remember that Ohm's law applies primarily to ohmic materials, where resistance remains constant regardless of the voltage or current. Many common conductors, like copper wires, are ohmic. However, some materials, like semiconductors or certain types of light bulbs, due to temperature changes, might not strictly follow Ohm's law across all operating conditions. But for basic circuit analysis, it's an indispensable tool. Step 8. Final summary and key takeaways. Ohm's law, V equals I times R, is the cornerstone of understanding how voltage, current, and resistance interact in an electrical circuit. It's a simple yet powerful relationship that connects the push, voltage, the flow, current, and the opposition to flow, resistance. Mastering this law is essential for building a solid foundation in physics and electrical engineering, helping you understand energy transfer and charge movement in virtually any electrical system. Thank you for joining me for this session on Ohm's law. If you found this explanation helpful, please give it a like, subscribe to the channel for more physics breakdowns, and share it with anyone who might benefit. Feel free to leave your questions or comments below. I love hearing from you. And if you have a specific physics problem you'd like to see solved in a future video, consider donating to the channel. Every month, I'll select a few problems to solve in their own dedicated videos.